All right. Okay, so we had skipped this problem so that we could get to the one on the next page. So it says pea plants have offspring with the following equally likely genotypes. So it's like there are two chromosomes. The dominant, they usually use the capital letter for the dominant gene and then the lowercase for the recessive gene. So you could have two dominant, the dominant from one parent, recessive from the other, or switched, the recessive from the first parent, the dominant from the second, or two recessive genes. And they say those four combinations are all equally likely. So it says if one is selected at random, what is the probability that the outcome is two dominant genes, capital A, capital A? So if they're equally likely, then we can use that classical approach. So we just do how many look like this out of the total number possible. So usually the denominator is the easier one. How many different outcomes are possible? 4, right? 1, 2, 3, 4. And how many ways are there to get two capital A's? 1, right? So 1 out of 4. Is then, by the criteria we talked about last time, is getting this like genotype unusual?
No.
No, why not? Right, this is 25%, so it's greater than 5%. Oops, let me fix that. Okay. So this is another one about genotypes here. So when Mendel conducted his famous genetics experiments with peas, one sample of offspring consisted of 428 green and 152 yellow. So they had, it was sort of this situation where green was the dominant and yellow was the recessive. And so the only time you would show the recessive trait is if both of your genes were the recessive gene. Because if you have the dominant one at all, like if you have a combination of dominant and recessive, that's why it's called the dominant one. That's the only one that shows, right? So the only way that they would show the recessive trait, the probability is 1 out of 4, right? The only way to get it is the two recessive genes, okay? So he theorized that if they were all equally likely, 3/4 of the time you should get the dominant, which was green, and 1/4 of the time you should get the recessive, which is yellow. So it says, based on those results, now he didn't know that at the beginning, so he just did a bunch of experiments. And so we're supposed to use his results to estimate the probability of getting an offspring pea that is green. So we want the probability of green. And when we do estimated probability, we do the number of times we got green divided by the total number of times he did the experiment. So what's the total number of times he got green? 428. And what's the total, how would we figure out the total number of times he did the experiment? Right, add them to, yep. So 428 plus 152. Yeah. So 580. Now, if my math lab wanted a fraction, remember, you just do so 428 divided by 580. And then you can do it right here. You can hit the math button, convert to fraction. It will simplify for you. So 107 over 145. Math, which is right under the alpha button. And then convert to fraction is highlighted, so just press enter, and then press enter again. Okay, so as a fraction, it's 107 out of 145. If we want it as a decimal, so close to 3/4, I don't know, let's look at it as a decimal because I know what 3/4 is as a decimal, right? So you can just hit math, convert to decimal. So about 0.738. So is that relatively close to 3/4? Yeah, because it's close to 0.75, right? So yes. So the next example deals with the drug Viagra. So it says, when it was clinically tested, 117 patients reported headaches and 617 did not, based on data from Pfizer. Use this sample to estimate the probability that a Viagra user will experience a headache. So we want probability of a headache. So again, if we're using their data, this is estimated probability, so it would be the number of times they observed headache divided by the total number of times they did the experiment. So what would go in the numerator? 117. And how would we find out what goes in the denominator?
617 plus 100%.
Yep, add those together and you get 734. And we can see if that simplifies. It does not. So that's the simplified fraction. If we want it as a decimal, just go down to convert to decimal. So about 0.159. Okay, so that's the first part. Is it unusual for a Viagra user to experience headaches?
16%.
Right. No, right? It's not less than 5% of the time. So not less than 5%, so not unusual. Is the probability high enough to be of concern to Viagra users? Well, I guess that might depend on the user, right? I mean, like, if you're talking about quality of life, maybe you will put up with a headache, you know, if it's working in other areas. So depends. Yeah, Sheila. Statistically significant. Would it be statistically significant? Right, statistically significant means the same as unusual, right? Practical significance would be like if the person who's a potential Viagra user would say, okay, now I'm not going to take it because I don't want to get a headache, right? That would be practical significance. Okay. Okay, so this is the probability high enough. That's really a subjective sort of thing. It will depend on the user. I mean, like if they said there's a 16% chance that you'll die, that's different, right? But getting a headache,
Even
you know.
1%.
Right, exactly, for death, yeah. All right, and then we did the next page. Okay, another genetics problem. So it says men have XY or YX chromosomes and women have XX chromosomes. So there are some X-linked recessive genetic diseases. One is color blindness. That tends to be much more prevalent in males than in females. So it's related to the X chromosome because then we'll see why they call them X-linked for men, or why that results in men having a higher incidence. Another one is this juvenile retinoschisis. It says a condition in which the retina separates into layers, so the part of your back of your eye. So these X-related or X-linked recessive genetic diseases occur when there is a defective X chromosome that occurs without a paired X chromosome that is good. So it says in the following, represent a defective X chromosome, defective with a lowercase x, because it's recessive, right? So use the lowercase. So a child with the XY or YX pair of chromosomes will have the disease because they don't have a good X to balance it out. And this trait is not carried at all on the Y chromosome, only on X's. Okay? So if it's a male and they have one bad X, they don't have a good X to balance it out. Okay? While a child with any of these other genotypes will not have the disease. They could be a carrier, but not have it because it's recessive. So if you have two good X, you're good. If you have a good X and a good, and a Y that doesn't even have that, you're good, or switch the order. Even if you have one bad X and a good X, it's still good. You won't ever have it. So it says each parent contributes one of the chromosomes to the child. And so part A says if a father has the defective X, now, so the father will have a defective X and then it has to have a Y chromosome. So I usually make a table. And so I put like the father's chromosomes on one side and the mother's on the other. So he has a defective X and then he has a Y, which really has nothing to do with the disease. And the mother has two good X chromosomes. Okay, so then you just fill in the table with the combinations. So this one is little x, big X. And so I just kind of put this little tail on the X, so because otherwise small x and big X kind of look the same. So I just try to put that little hook kind of on the end so I can distinguish between lowercase and capital. And then this one, we're getting a little x from the father and a big good X from the mother. And now the bottom row, we'd have a Y and a capital X, and then here we'd also have a Y and a capital X. So the top row, two X's, those are daughters. And the bottom row, X and Y, those are the sons. So what is the probability that the son has the disease? 0, right? There's no way he could get the disease. Now B, so same scenario, so we can use the same table. The father has defective X and the mother has good X, both of them. What is the probability that a daughter will inherit the disease? 0, because she has a dominant one to counteract it. Okay, so now C, they changed the scenario, so I need a new table. Okay, so the mother has one defective X and one good X, and the father has good X and then a Y chromosome. So good X and a Y, which doesn't affect the disease at all. And then we want to look at the combinations, okay? So we have a big X and a little x, and a big X and a big X. And then here we have a Y and a little x, and then a Y and a big X. So these are daughters, top row, bottom row, sons. So probability son has disease. Now, okay, I want to kind of distinguish what they're asking here. They're not saying what's the probability that one of their children will have the disease. If they said what's the probability that one of their children will have the disease, what would the answer be? 25%, because only this one would have the disease. They're saying what's the probability that a son has the disease? Right, so it'd be 50% because there are only 2 possibilities for a son, right? And one of them has the disease, so 1/2 or 50% or 0.5. And then part D, we'll use the same table. What's the probability that the daughter will inherit the disease? 0. Right? So the key is the daughter always gets, since the daughter has 2 X's, the only way the daughter could get it is if both, the father would have to have the disease, right? And then the mother would have to have at least one defective chromosome.
Probably.
Okay, so here a roulette wheel has 38 slots. So this is if you like gamble. One has a 0, another has a double 0, and then the other slots are numbered 1 through 36. So it says you place a bet that the outcome is an odd number. So, one thing, and I think they say this on the homework, is they don't count these as odd or even. So not considered odd or even. 0 really is an even number, but for this particular game, they're not counting them.
So is it true that in a very, very high math, you can divide it by 0?
You can. But sometimes you get an answer and sometimes you don't.
Okay.
But you can have 0. Okay, so what's your probability of winning? So you think of how many ways there are to win divided by the total number of outcomes. So what's the total number of outcomes? 38, right? Because it could land on one of 38 slots. Okay, so how many of them would be even? So now these aren't. So then we have these 36 numbers. How many of those 36 are going to be even? 18. Half are even and half are odd. Right? So 18 out of 38. Your calculator will simplify this to be 9 out of 19. I'm just going to leave it as a fraction. Part B, what are the odds against winning? So when they do odds against, Monday, we talked about odds in favor. So if we were doing odds in favor, the numerator always went first. So odds against, the numerator goes after the colon. Okay, so 9 goes after, and I'm going to use the simplified fraction. So if there are 9 ways to win, how many ways are there to lose? 10, right? Because this is in the simplified form. They're saying there are a total of 19, right? 9 are winning, which means 10 are losing. So 10 to 9. Part C, when you bet that the outcome is an odd number, I think I might have said even before, but the probability of winning, whether it's odd or even, is the same, right? Because there are 18 of each of them. Okay. The payoff odds are 1 to 1. So that means how much you bet is how much you win. Exactly, they match it exactly. So how much profit do you make if you bet $18 and win? $18. Then part D, how much profit would you make on the $18 bet if you could somehow convince the casino to change its payoff odds so that they are the same as the actual odds against winning? Well, if we had looked at like the original fraction, so the 18 matches what we had in the numerator. So if I would have set up the odds with having 18 second, what would go first? I'm doing odds just based on this fraction. So if there are 18 ways to win, how many ways are there to lose? 20, right? Because there are 38 possible outcomes. So if 18 win, then 20 lose, right? So this is saying if you bet $18, you should get $20 back. Right? That would make it fair. Since the odds are 20 to 18, if you play and win, they should pay 20 to 18. But casinos don't do that. They set it up so they win. All right, so that is it for 4.2. 4.3 is on what's called the addition rule. And the first thing we get is a definition of compound event. So a compound event is an event consisting of more than one outcome. So like here, when I have this table, so I do the household type, and so they talk about a family where there's a married couple, and then a family with a male head of household, no wife present, and then female head of household, no husband present. And then whether or not they're above or below the poverty line. So here, see, they talk about two different things, married couple, family, and below the poverty line. So that's a compound event. I have to focus on two different things. Okay, so that's what they mean when they say compound event. We talked about mutually exclusive last time. It's impossible for both events to happen at the same time, or there's like no overlap, right? The general addition rule is as follows. So for any two events, E and F, the probability that E or F happens is, okay, so before we do that, before I look at that formula. So suppose I had brought treats today because it's Valentine's Day. Suppose I brought 18 cookies and 20 cupcakes. So the first person, and I said, you get to choose one thing. So when I say you get a cookie or a cupcake, so the first person that comes up, how many choices do they have? 38, right? We add them together, okay? So that's why the word or, and we'll see this more, the word or goes with plus. Now this subtraction thing I'll get to in a minute. Why is there a subtraction part? And I'll get to that. Okay, so this table comes from 2016 data that relates to poverty levels and is from the census website. So I just give the website there. And they say, like in the description of the study, that it's not 95,000 people, it's 95,000 randomly selected addresses across the US. So they picked an address at random. So they could get more than one person when they pick an address. Okay, and so these are some of the results here. So the household type, they classified this way. And I say this data is from 2016 after most states have marriage equality. So the married couple, that could be same sex or opposite sex couple. There's no distinction there. But then when they talk about head of household, I say, why do you think the last two rows mention male no wife and female no husband? Like, why don't they say male no wife or male no husband? So think about what they're measuring. They're measuring poverty, right? So what do we know about earnings?
So they're leading it up.
Right, right. So two men would have higher earning power than like, what am I trying to say here? So two men, so if there's another man, he generally has higher earning power. So it's especially the female head of household, no husband present. So even if there was another woman, there's likely that she earns less than a male counterpart, right? So that's why, even though there are obviously male heads of households that they would not even want a wife present, right? So they're talking about the difference in earnings between the genders. So that's why they classified the households this way. Okay, so because of gender differences in earnings. And they didn't give so they said married couple family, and so I don't know necessarily why they didn't do like non-married couples, like they didn't separate out non-married couples that are living together. They just didn't. This was how they had the data arranged. Okay, so here it's what.
Oh, there's also another argument. If a woman is pregnant, she doesn't generally work at least a month or two after the before after the birth. So that could be a fact in it too.
Yeah, good point. Yeah, right, because there wouldn't be somebody there necessarily picking up the slack.
They don't give birth, so they can
right.
12 months.
Yeah. Okay, so here, determine the probability that a randomly selected family fit the category married couple below the poverty line. So it's not married couple or below the poverty line. It's married couple below the poverty line. So I'm just going to abbreviate married couple MC and then BP below poverty. So I'm not using this formula they gave at the top of the page. I'm just looking at this. So what I want is the number of times I saw a married couple below the poverty line divided by the total number of times I did the experiment. So what's going to be in the numerator?
3096.
3096, because here's married couple below the poverty line. So 3096. How am I going to get the denominator? Yep, we have to add up every single number in the table. I'm actually gonna, what I'm gonna do is I'm gonna add a row at the bottom. I'll add down, I'll add across, so we have like all these totals. Okay. I don't know that that I need all of these numbers. Ooh, this is something. That's great. I forgot a digit. Okay. So either way, the total for everything is 82,854. And I'm just going to get this as a decimal. So about 0.0373. So that would be about 3.7% of the households in the survey for a married couple living below the poverty line. Now the next one says, determine the probability that a randomly selected family fit the category male, this HOH means head of household. So fit the category male head of households, no wife below the poverty line, or female head of household, no husband below the poverty line. So I'm just going to call this, because I don't want to keep writing that all the time, I'm going to call that E, just because those are the letters they use up here. And I'm going to call this whole thing F. So we want the probability of E or F. So using the formula at the top of the page, we get the probability of E plus the probability of F minus the probability of E intersect F. Oh, E and F, sorry. I'm using symbols I haven't introduced yet. Okay, so the probability of E, male head of household, no wife, below the poverty line. So we already know the denominator is going to be the total, which is 82854. Now, how many times in the experiment did we run across a household that was male, head of household, no wife, below the poverty line? 847. Plus, and then this one will still have 82854 in the bottom. And how many times did we run into female, head of household, no husband, below the poverty line? 4138. Now, E and F, you just have to ask if those two things could happen at the same time. Could you have male head of household, no wife, below the poverty line, and female head of household, no husband, below the poverty line? Like in the same house? In the same address?
Yeah, if they're renting out. Or cousins.
This is true. So I am right. So let's think about like individual records. You're right. So if you look at an address, that could happen, right? So here the number of, so they were looking at families, okay? So right, per address, you could have both things happen. Like if it was like a duplex or apartment or something. Right, per family, you can't have a male head of household, no wife, and female head of household, no husband in the same family, right? Okay, so those two are mutually exclusive, so there would be 0 of those. So I think on the next page we'll see why the subtraction part comes into play. And so then we just add these two fractions together. So about 0.06. So more likely that a family is living below the poverty line if it's not a married couple than if it were a married couple. Okay, so Venn diagrams. Venn diagrams are used to visualize sets and relationships between them. So it says we almost always use a circle to represent a set. And then the box is like the collection of everybody. Okay, so the box is our whole sample. So in this picture, suppose we let M be the set of married couple families, and we let P be the families below the poverty level, okay? And we can use the following diagram to represent this situation. So it says some people, and I guess I really mean families, will belong to both sets, and some families may not belong to either set. So that's if the families aren't either married or below the poverty level, then we represent them just like still in the box because they're still in our sample, but outside the circles. So where you want to do is you want to start in the middle. You want to start with the people that fit into both circles. How many married families are there that are also below the poverty level? married couple families. And I have the table right here on the same page. 3096. Okay, and then what would go in this part of M's circle, do you think? Yeah, the 57725, right? Because these are still married couple families, but they're not in poverty, so we want it to be outside here. Okay, so now I want the people who live below the poverty line, but they don't belong to the married couple circle. So what numbers would we use to get this part of the P circle?
The 8081.
So no, just these two, because I don't want to count the 3096 again,
okay.
Right? So So 4985. And so notice if you add these two numbers together, the 3096 plus 4985, you get the 8081. That was the total here, right? We just had to take out the married couple families. Okay, now we have to figure out how many people are outside of either of the circles. So I'm going to sort of identify which numbers I've already used. I've used the 57,725. I've used the 3096. I've used the 847, and I've used the 4138.
So it's 5605.
Yep. So 17048. So it says, use the Venn diagram to find the probability that a family fits the description of married couple family. I'll just call that M. Or is a family that is not below the poverty line. So I'll use the letter R. So we want to find probability of M or R. I chose R. Not that you're rich if you're not below the poverty line, but that's sort of what I was thinking. What's the opposite of poverty? Okay, so the formula says P of M plus P of R minus P of M and R. Okay. So married. What's the probability that when we choose a family, it's a married couple family? Well, we still have a total of, was it 82254? 82854. How many of those are married couples?
60821.
Yep, the 60821. And then, okay, so the probability they're not below the poverty line. Well, if they're not below, then they're above, right? So how many families are above the poverty line? Yeah, I'm just going to do the total here. Yeah, the 74773. So I'm going to use a highlighter here. So for the married, and I'm going to look at the table maybe instead of the Venn diagram. So when I did the probability that they're married, I looked at these two numbers. When I looked at the probability that they're not below the poverty line, which means they're above the poverty line, I looked at these three numbers. So you can see that I've used this number twice. I used it here and here. That's why we have to subtract it off once, because we counted those people twice. So we just have to subtract it off so that we don't double count. So the number that I used twice was the 57725. And then what I'm going to do when I type this in, I'm not going to type those three fractions in separately because they have a common denominator, right? So I'm just going to do the numerators in parentheses, 60821 74773 minus 57725, close parentheses, and then divide it by that denominator. And decimal is fine. So about 0.94. So about 94% of people are either in a married couple family or are in a family that's above the poverty line. Yeah. Okay, so here we have 3 pairs of events, and we just want to say whether they're mutually exclusive or not, okay? So, and then we're thinking about doing one trial. So when we do one trial, could possibly both of these things happen? Like if I look back here, is it possible for me to select one household, one family, and get male head of household and below the poverty line? Yeah, because there are male head of households below the poverty line. So those would not be mutually exclusive, because I could have both things happen within one family, okay? So here, they say you're conducting a Pew Research Center poll, and then the first event is that you randomly select a subject who is a Republican, and let's assume registered Republican, okay? And then B is you're conducting a Pew Research Center poll, and you randomly select a subject who is a Democrat, and again, let's think registered Democrat. So could you do the trial one time, pick a person, and have both of those things happen?
Unless it's a person with,
You can't register, they won't let you register. Yep. So these are mutually exclusive. It depends on the state. Like Minnesota, we're about to change to primaries. And then with primaries, it's different that we had been a caucus state up until now. In caucus, you can pretty much go wherever. But primaries, like South Dakota, is primary. So you have to be, like if you want to vote in the Republican primary, you have to be registered Republican. Even independents can't vote in the in the Republican primary. Okay, so the next pair of events. So the first thing is randomly selecting a movie with a rating of R, and then event B is randomly select a movie with a rating of 4 stars. So think of, if you select one movie, could both of those things be true about the movie?
Absolutely.
Yes, you could have, yes. So these are not mutually exclusive. And I'm just going to abbreviate. Okay, what about the next pair? Randomly selecting a college graduate, randomly selecting someone who is homeless.
No, there are some weirdos.
Don't say weirdos.
Well, who study too much and then they decide that they just get too much indoors and they want to be outside and they're homeless.
But it could be.
There are some movies about it.
But there can be other circumstances where they're not like don't make that decision, right? You can be homeless without making a decision to be homeless. So the question is, are they mutually exclusive? No, because you could have one person selected at random who's a college graduate and is homeless, right? So they're not mutually exclusive. Okay. For the next two questions, it says use the data in the accompanying table, which summarizes challenges by tennis players based on data reported in USA Today. So the results are from the first US Open that used what's called the Hawkeye electronic system for displaying an instant replay used to determine whether the ball is in or out of bounds. Okay, so it says in each case, assume that one of the challenges is randomly selected. So if M denotes the event of selecting a challenge made by a man, find P of, remember this means the complement of M. So what would the in words, what would the complement of M be? Right, it was made by a woman, right? If the challenge wasn't made by a man, it was made by a woman.
So M complement means manly or women?
So M is, it's made by a man. So M complement is the opposite of that.
So they complemented women to win.
So it's just the opposite. So if a man didn't make the challenge, then a woman made the challenge. Right? The complement kind of means like put the word not in front of it, so the challenge was not made by a man. Okay, so P of M complement, and if you want to think of it as the probability that it was made by a woman, the challenge was made by a woman, all this table, everything is a challenge, right? So first of all, we would want to find the number of challenges made by a woman divided by the total number of challenges altogether. So, right, 126 plus 224, 350? Okay, so these add up to 489. These add up to 350. And so we would have to add these together to get the denominator, right? So 350 plus 489 was it 839? So about 0.417. So about 42% of the challenges were made by women. Okay, so here we see the word or in the next one. So I'm going to say challenge was made by a woman. I'll call that W. And then not successful, I'll just call that N. So we want the probability of W or N, which is the probability of W plus the probability of N minus the probability of W and N. We already know the probability of W, right? We just found that in the last problem. So 350 out of 839. Okay, not successful. Okay, well, I know 839 is going to be in the denominator. What's going to be in the numerator? What numbers are we using?
288 plus 224.
Yep. But then, okay, so when we do that for the women, we did these two numbers. For the not successful, we did these two numbers, which means we've used the 224 twice, right? So that's why we're subtracting off the 224. So again, I'm just going to add the numerators. Oops, there's a minus in between there. I'm going to do just the numerators and then in parentheses and then all over the denominator. And in fact, I can just cancel the 224s right now, right? So 350 plus 288 all over 839. So about 0.76. Okay. So here it says, use the following table summarizing results from a study of people who refused to answer survey questions. So what they did is they categorized them by age group, okay? So the 18 to 21 age group, 73 people responded and 11 refused. 22 to 29, 255 responded, 20 refused, and so on, okay? So it says, a pharmaceutical company is interested in opinions of the elderly because they are either receiving Medicare or will receive it soon. What is the probability that the selected subject is someone over 60, someone 60 and over who responded? So probability 60 plus, and they're not saying or responded, 60 and over, they responded. So first of all, what am I going to put in the numerator? 202. 202.
Over 251.
Not just over 251. Yeah, we have to add everything together. So here's 84, 275, 278, 152, 65, 2. So over 1,205, and I'll just get that as a decimal. So about 0.168. So close to 17% of the people in the survey were people that were 60 and over who responded. Okay, so the next one, they give us all the information just in words. We want to make the table ourselves, okay? So this is a totally new problem. So it says, use the results from the one-panel THC test for marijuana use, which is provided by the company Drug Test Success. So let's see here. So I'm going to make my table. So we have positive test results and false positive test results, and then negative and false negative. Okay, so I would do, let's see. Yeah, and okay. So for the, right, so, yep, false positive. So if we have like positive test results, negative test results, so we'll do the ones that came back false, right? And then the ones that came back true, right? The test was good. So it says there are 143 subjects with positive test results. So think of a totals column as well. So I have my table plus totals over here on the bottom and totals to the right. So first, I'm going to number like the boxes in my table, and you guys are going to tell me which box I should put the number in. Okay, so I don't know if you can see this, but I did 1, 2, 3 on the top, 4, 5, 6, 7, 8, 9. Where should 143 go? 1 through 9. Tell me which box. 7, right? Because this is all of the positive test results. It doesn't say they're true, right? There were just a total of 143 positive results. So where does the 24 go? Box 4, right above it, right? Okay.
It's a false positive.
When it comes, the test comes back positive, but the person really hadn't used the drug. So where does the 157 go? Box 8. Yeah. And then 3 false negative. 5 right above it. Yep. Okay, so we have 5 boxes left. So how am I going to get box 1, the one in the top left corner? Yep, 143 minus 24. 119. Okay, and then what's going to go in box 2? Yeah, 154. And then how am I going to get box 3? Right, just add straight across. 273. And then the same thing, the next row will be 27, and then 300. And it doesn't, it doesn't matter if you add down or across, you get 300. So that means there were a total of 300 people in the study. So it says if one of the test subjects is randomly selected, find the probability that the subject tested positive or used marijuana. Okay, so first of all, when I say tested positive, that's pretty easy. We can tell from our table what tested positive is, but I don't have any part of my box that says used marijuana or didn't use marijuana, so. Okay. So, would this one be from a person who used marijuana? Yes. Positive test result, and the test was true. That means they used. Okay. Would this one be used? No. So the test was negative, and it was true. So did they use?
Yeah.
No. The test is true. The test said no, they didn't use it, and the test was true. Okay. What about here? No, because the test came back positive, but it was false. So they didn't use. So what about the 3? Yeah. Yes. The test came back negative, but it was false, which means they actually did use. Okay, so those are the people that used. Okay. So, test positive, because I just don't want to put probability, have a P outside and a P inside. And we'll talk about false positives and false negatives later in the semester as well. Positive test, I usually do a T with a little plus on it. Okay. And then use marijuana, I'll just use the letter U. So they want us to find the probability that the test was positive or they used. And the formula we have from the previous page is the probability the test was positive plus the probability that they used minus the probability the test was positive and they used. We know all of the denominators are 300, right? What goes in the numerator for positive test? 143. right? Yep, that's the total for positive tests. There were 143 positive tests. Now, the probability that they used, so what's the numerator there? That's the 122. Now, probability that they tested positive and they used. What's?
Oh no, 143 plus 122. So
right, tested positive and they used, which means it's, I highlighted it in green, right? So it's just 119. So again, I'm just going to add up the numerators in parentheses and then divide by 300. Okay, so about 0.487. All right, I think, okay, so you'll just hang on to the 4.4. So remember, Monday is a holiday and Wednesday is the test. So you'll have to hang on to this until the following Monday. So don't lose them because I don't get extra copies.